Hi everyone. Today I'm going to be talking about a feature of the FQL tool called Computational Schemas. So let me see, screen share, open PDF. All right, and begin. Okay, so as I mentioned, we'll be talking about computational schemas, and obviously this is 2016, but not 2015. Anyway, so we'll start by reviewing just the basics of the Factorial data model. Just schemas as categories. We don't need the data migration stuff for this talk, but this talk does extend the introduction to Factorial data migration talk that you can find in our YouTube channel. And the basic idea here is that the more recent languages in the FQL family of languages can compute in schemas and by extension within queries and data migrations and other places. And this is programming language integration essentially. So these computational primitives are user defined using equational logic and optionally a binding to some Java code. So this also, in addition to being integration with a programming language, provides a way to integrate the FQL tool with other pre-existing code bases. So some examples of this are we can do computation that involves Boolean algebra or arithmetic, addition, subtraction, stuff like that. You can manipulate strings, images. You can even do machine learning. I'll elaborate on that. And all kinds of sophisticated computational primitives can be built in. And I'll just mention in passing that our way of bringing programming language integration into our technology is a kind of dual to another approach called LINK of integrating programming languages with databases. And so there's a paper on the archive. You can read at that link there. It goes into some of the details. So anyway, just a real quick review of the Factorial data model, because just the schemas and instances part are all we're really going to need for this talk. The slogan here is that database schemas are categories, which means that we think of schemas as being defined by directed multigraphs that are labeled along with equations between paths. So here is an example where our schema talks about employees and departments. So there are two nodes. Those are the dark filled in circles, emp and dept. The directed edges, manager, works in, and secretary, are foreign key relationships. So manager takes employees to employees. Secretary takes each department to an employee that is a secretary, and each employee works in a department. There are path equivalences, which are data integrity constraints or business rules. So these in particular say that in the lower right, a department secretary works in the same department that they are the secretary for. And in the lower left, that an employee's manager works in the same department that the employee does. And then finally, you see some open circles in the graph, first and last for emp and name for dept. These are the attributes for those entities. So employees have first and last names, such as the imaginative Al Aiken, Bob Bowe, and Carl Cork, and departments have names such as CS and math. And then in the lower half of the screen is an instance on that schema, which mathematically is a set-valued functor, but it can be thought of just as a set of tables. There's one table per entity, per filled-in circle, so emp and dept. There's an ID column that gives the employees. So for example, there's 101, 102, 103, 3 employees, Al, Bob, and Carl, 2 departments, and then the columns are just filled in according to the arrows in the schema. So employee 101's manager is 103, for example. That is all we need to know about, all we need to review about the Factorial data model to talk about computational schemas. So in particular, let's call the top part that I just showed you, just the graph, the directed labeled multigraph. Let's call that the signature part of a schema. And let's separate it from the data integrity constraints, the equations. And for this talk, rather than write equations between paths, for example, emp.manager.works equals emp.works, we're going to use a logical notation because it'll make things easier in the long run. And so in the logical notation, these path equivalences just mean, for example, for every employee E, the manager of E works in the same place that E works in. And similarly for departments. So this is really just a change in notation. The meaning hasn't changed. And this notation is a little easier for us because we're going to start to talk about things like addition and subtraction, which are binary operations. So anyway, in the logical notation, we can think of the attributes and the foreign keys as being unary function symbols. So for example, what is name? It's a function from the set of departments to the set of strings. What is manager? It is a function from the set of employees to the set of employees. And the basic idea behind computational typesides is that we say that a schema exists in an ambient equational theory, which we call the typeside. So for example, that schema that talked about employees and departments can be thought of existing in an ambient typeside for arithmetic. So that means that we can think of it as existing within an equational theory that has a sort nat for natural numbers, just like it had a sort for employees and a sort for departments, and which has function symbol 0, which is a nat, successor, which is a unary operation from nat to nat, and plus, which is a binary operation. So morally, there's not a lot of difference between 0 successor and plus compared to manager, works in, and department. They're all just function symbols, and there's morally not much difference between nat, the sort nat, and between employee and departments, those sorts. And so just like we had data integrity constraints about managers and works in and secretaries, we have equations for this arithmetic typeside that says that for every natural number n, that n plus 0 equals n, and that for all two natural numbers n and m, that n plus the successor of m equals the successor of n plus m. And these two equations actually define addition outright. So this is exactly what you would write if you were implementing unary arithmetic in a functional programming language. And for the purposes of this talk, we're just going to assume we have a function symbol called length that gives the length of a string, presumably as a nat rather than an int. That's a small typo. And what can you do with that? Well, the key idea is that when we define a schema, we can just say that this schema exists in a particular typeside, and then write data integrity constraints that mention the typeside. So here's an example. It's the same schema as before with a small difference, which is that the last name attribute has been replaced with an attribute called len for length. And we've also added a data integrity constraint that says for all employees E, len of E, so that attribute for E, is length of the first name of E. So length here is a computational primitive that we were assuming based on the previous slide, and an instance that can live on this schema, then in its len column would have the lengths of Al, Bob, and Carl's, the names. So Al is a length of 2, Bob is a length of 3, and Carl is a length of 4. So in this way, we can embed essentially arbitrary computational content into schemas. And for those who are interested, there's a paper called Algebraic Databases. You can get it from the website that talks about this in detail. A key point that I want to bring up is that these attributes like len can be computed based on the other entries in the instance. So in particular, every instance in FQL can be partial, and each such partial instance has a unique completion. So what that means is if you give the FQL tool an instance that is missing all of its data except for the length of the names, then the tool will actually use that equation, len of equals length of the first name, to fill in the missing value. So you can think of this as being a derived column, if you will. And from the point of view of the tool, there's not a whole lot of difference between a derived column and a non-derived column. If a column needs to be derived, it will just derive it and be done with it. So that's pretty useful, the ability to define computational primitives using equations, but it turns out that the FQL tool has additional capabilities. So as you might imagine, to implement things like arithmetic, we may not want to work in a unary representation with equations. We might want to define addition to mean, for example, the addition that Java does. Or we might want to invoke other computational primitives rather than define them using equations. And so the FQL tool lets you do that. You can bind those function names like plus or length to classes in Java. And in this way, we've been able to do some interesting experiments. For example, we have a project now, it lives on GitHub by the name FQLML, that uses a machine learning library. And so we've been able to use computational schemas and the derived column behavior to actually use that library to do machine learning. So this is a screenshot of the tool. It's a built-in example where it has 8 people with different ages, and it's trying to classify them into old and young. And this example is fascinating because it reveals the interplay between the computational type sides and the null or the unknown, the partial values that you can put in these FQL instances. So here in particular, person 0 and 1, they are classified as young, and persons 6 and 7 are classified as old, and then the other ones are classified as nulls symbolically. So what is the input class of P2? Well, if you look at the image there, it's input class P2. So you can think of that as a null. And then we used a equation similar to the length equation before to have this machine learning library do some kind of nearest neighbor classification or some such thing. And what's interesting here is that you see that, for example, it classified P2 is young, and then the output classifications of the other some of the other values are dependent on the unknown input classifications from the input class column. So this is essentially doing a combination. It's doing classification based on symbolic values, which is, well, I find it fascinating, but it has some interesting behavior. For example, the input classification of P3 is not used in the output classification at all. And the input classification for P2 and P5 appear twice. So it's not entirely sure what how it was doing the classification, but some very interested emergent behavior really is possible when you combine the computational type sides with the unknown. The fact that the FQL tool is very good at handling unknown values. So anyway, just to conclude, the way computational schemas work is that we essentially say that schemas, like our employees schema, they all live in a user-defined computational context, and those contexts have additional types, things like nat and string, and symbols, things like plus times, length, and equations that define them. And optionally, those symbols, such as addition, can be bound to user-provided Java code. And these computational primitives, attributes, foreign keys, these all mix freely in a correct way, and can be used to do some interesting thing, like doing machine learning to generate derived column values. So anyway, that's it. I'd encourage everyone to check out the algebraic databases paper if you're interested in learning more, or to try out some of the examples in the FQL tool. A lot of them are doing computational schemas nowadays. Anyway, thanks.